Okay, we're now ready to do problem number 4, which is the first of two where we actually calculate the properties for a chemical reaction. I've chosen for this example the simplest chemical reaction I could come up with, which is two iodine atoms reacting to form a bond and form an I2 molecule. The reason that's advantageous is the partition functions for the iodine atoms, of course, are especially simple, so that'll shorten up our calculation quite a bit. I chose temperature of 298.15 and a standard state pressure of 1 atmosphere. I chose those values because those are the table conditions. So the numbers we get will be comparable to numbers from the tables. We can see how well we're doing. Also note, because it will be important, the number of moles on the product side here is just 1. The number of moles on the reactant side is 2. That means delta N for this reaction is -1. That comes in at several points during the course of the calculation. We're going to want to calculate two different things, really, or two batches of things. One is the equilibrium constant, which, as we saw earlier in the notes, can be divided or broken up or factored into a whole bunch of smaller equilibrium constants, each one of which has to do with just one type of motion in the molecule: translations, rotations, vibrations, and electronic motions, plus this ZPE, or bond energy factor, at the end. And so we'll calculate each of those. And then in the next part of the problem, we'll calculate all the relevant thermodynamic quantities. We did that with both HCl and N2 above, but now these are delta G's and delta A's and delta S's and delta H's and delta S's for reactions. So these are not absolute values anymore. These are now the changes that take place in the course of the reaction. And again, 3 of these values, the delta G, the delta H, and the delta S, are exactly the values we can compute from the table values, so they're comparable. We're going to need some molecular data for each of the species in question now, right? Before we just needed molecular data for one molecule, but now we have 2 different kinds of species. We've got the I atoms and we've got the I2 molecule. We need data for all of those things. So the molecular weights, the electronic ground state degeneracies. Notice that the iodine atoms have a pretty high degeneracy. That's because anytime you've got anything that's really reactive and really unhappy, basically, then the degeneracies can start getting high, and that's especially true for lone atoms like the iodine atoms. We need the vibrational temperatures, we need the rotational temperatures. Notice that there's no vibrations or rotations for atoms. That makes things easier. And then we need the D0 values. As I explained earlier in the notes, those are used essentially to calculate the change in the ZPE, or zero-point energy terms, that play an important role in the equilibrium constants and also in other quantities. All right. So the first part of the question, part A, is to calculate all the factors in the equilibrium constant. For the translational equilibrium constant, we have a nice formula, 0.46009 T to the delta N power times basically molecular weights, but for each of the contributions in turn. So molecular weight for I2 over molecular weight for I, but there's 2 of those, so squared, and then all of that to the 3/2 power. So if we plug numbers into that, that's 0.46009 times 298.15. Delta N is -1, so that's to the -1 power. Molecular weight for I2 is 254, and for each of the i's is 127, and that gets squared, and then all of that to the 3/2 power, and that turns out to be 1.230 times 10 to the minus 6. Notice that it's a small number. What that means is that as far as translations are concerned, the contribution is unfavorable to the reaction. That's because, of course, we started out with 2 atoms, 2 independent particles, and we end up with only 1. So we lose 1 batch of translations in the course of this reaction, and that's reflected in this negative, well, this small value for Kt. Next factor is Kr. Always these factors are as if you were writing an equilibrium constant with concentrations, but you use partition functions instead. So for Kr, it's going to be the Qr for I2 over the Qr for I squared, because there's 2 i's. That's equal to, for I2t over 2, right, because that's the symmetry factor, theta r over t over, no, sorry, there are no rotations for atoms, of course, and so those get a 1. Whenever you're dealing with atoms or something that doesn't have a degree of freedom, the partition function is just a 1, so 1 squared down below. And so that's just t over 2 times theta r. That's equal to 298.15 over 2 times 0.0537. That's the rotational temperature, really low for iodine, of course. And that is equal to 2776, about 3,000, 2,800. Favorable states for the rotational contribution to the equilibrium constant. That means, of course, that in going from atoms to I2, we gain rotational quantum states. And that means that the effective contribution to rotations in the equilibrium constant is favorable. Of course, the opposite is happening up here. I plus I goes to I2 means we're losing translational states here, and that's why that factor is unfavorable. All right, the next one is the vibrations, Kv. That's equal to Q vibrational for I2 over Q vibrational for the 2 iodine atoms squared. But there are no vibrations, so those are 1s again. And so that's, I'm just going to assume that that's 1 or treat that as 1 right away. So that's just QV for I2, and that's equal to 1 over 1 minus e to the minus theta v for I2 over t. That's equal to 1 over 1 minus e to the minus 308 over 298.15, and that is equal to 1.553. So again, the vibrations are favorable because, of course, in going from atoms to a molecule like I2, there are no vibrations over here. There are over on the product side. So we gain some vibrational quantum states as we go through the reaction, and that's reflected here. Of course, we don't gain very much vibrational quantum states because there just never is much population of the vibrations at room temperature. Finally, Ke, assuming that there aren't any contributions from excited states, well, it's QE for I2 squared over QE, sorry, not squared, QE for I2 over QE for I squared. And that's just the ground state degeneracies. For I2, it's just 1. And for the iodine atoms, it's 4. The ground state degeneracy is actually 4 for the iodine atoms, so that's 1 over 16. So in this case, we actually lose 16 electronic quantum states in going from the atoms to the I2 molecule. And so, believe it or not, the second biggest contribution after the rotations is the electronic contribution in this case because of ground state degeneracy in the I atoms. Finally, we need this ZPE factor or bond energy factor. Delta E ZPE is equal to minus delta D0 for this reaction. That's equal to D0 for I2 minus D0 for I2 minus 2 times D0 for an iodine atom. But D0 for an iodine atom is 0, right? Because it's not a molecule. There is no bond energy. And so that's just equal to minus D0 for I2. And that's equal to minus 149,000 joules, or 149 kilojoules per mole. And the overall factor is e to the minus delta E ZPE over RT, which is e to the minus 149,000 over 2479, which is equal to 1.268 times 10 to the 26th. So as usual, the bond energy factor is the dominant one in this case. Putting everything together, remember that we're using molar concentration as our standard state in this case, so this is a Kc value. Multiplying all those factors together, we get 1.230 times 10 to the minus 6, that's Kt. 2776, that's Kr. 1.553, that's Kv. And now 1.268 times 10 to the 26. 1/16, that's Ke. And then times 1.268 times 10 to the 26. That is the ZPE factor, or the bond energy factor, and that gives us all together 4.202 times 10 to the 22 for the equilibrium constant for the formation of iodine molecules from iodine atoms. That's a fairly large equilibrium constant, but that's not too surprising, right? Because this reaction ought to be very product favored, right? If we're forming iodine molecules from iodine atoms, that ought to be a favorable reaction. There's no chemical bond at all to start with, and we have one at the end. And so we ought to get a favorable equilibrium constant from that. There is an issue. As I pointed out earlier in the notes, this is a Kc value. But if we want to compare things to stuff that's in the tables, we need Kp values, because the table will be assuming 1 atmosphere as their standard state rather than 1 molar concentration like we did. So we got to convert. The Kp value is always equal to the concentration that you use as your standard state, RT, over the new pressure that we want for our new standard state, to the delta N power times the Kc value that we've actually calculated. This is a 1, C0 is 1 molar, P0 is 1 atmosphere, and RT is 2479, since we're at 298 K. Delta N is minus 1 for this reaction, so this becomes Kp is equal to Kc over 1 times 2479 over 1. Oh, sorry, I take that back. This 2479, we have to keep the units consistent, right? We need to use liter atmospheres for this, so this is 0.08206 times 298. And so, sorry, let me rewrite that. that is equal to, well, if you do the calculation out, that turns out to be 24.47. So the Kp value is just about 25 times smaller than the Kc value, and that turns out to be, when you plug the numbers in, 1.717 times 10 to the 21 is the value for Kp. All right, that's all of part A. In part B, we're going to calculate delta G of reaction, delta G0 for reaction, delta, let's see what we have here, yeah, delta A0, delta H0, delta U0, and delta S0. So we're going to calculate all of the relevant thermodynamic changes that take place during the course of the reaction. And we can compare three of these, as I set up above, three of these, not that one. Delta G, delta H, and delta R, we can all compare it to calculations from the tables. So this is part B. For delta G of reaction, we can use minus RT log of Kp now, right, if we want to compare to the tables. If we put a Kc value in there, that would be fine, but that would give us, there's nothing wrong with that, but it would give us a delta G value for a 1 molar standard state, so it wouldn't be comparable to the tables. So let's use the Kp value. In that case, it's minus now 24.79 for 298 K log of 1.717 times 10 to the 21, and that gives us minus 121.21 kilojoules per mole for the delta G, the standard state delta G change for this reaction. If we do this, the calculation using the tables, that's over here on the other side. Let me just show that value. Here it is. So here's the calculation from the tables. I plug in delta G's of formation here that I got from the tables in Appendix A in the back of the book. You do the calculation and you get 121.1 kilojoules per mole minus 121.1. So almost exactly in exact agreement with our calculation. That's, again, that's always satisfying. All right, delta A, the Helmholtz free energy change. What's that? Well, we have that delta G is equal to delta H, right? We don't know that value, but that's what it is. Minus T delta S for reaction. We're going to use that later. But for the moment, this delta H is delta U plus delta PV minus T delta S of reaction. And now we combine the T delta S and the delta U, that's delta A. Delta A of reaction plus delta PV. What's delta PV in this case? Well, it's an ideal gas, so delta PV is equal to delta nRT. T is a constant, so that's the mole number change times RT, and the mole number change is -1, so that's just minus RT. So overall we have delta A of reaction is equal to delta G of reaction, now switching this over to the other side, plus RT, and so that's equal to, we have delta G, it's minus 121.21 kilojoules, plus RT is 2.479 kilojoules, right? That's 2479 in kilojoules, and that is equal to minus 118.73 kilojoules per mole. All right, so now we have the delta G value and the delta A value. Let's do the one that's a little bit of work now, delta UR. There's no fancy way to do this. We have to use the energy calculation formulas to do this. Delta U of R is going to be equal to U for I2 minus 2 times U for the iodine, and that's going to be equal to U for translations for I2 plus U for rotations for I2 plus U for vibrations for I2 plus U for electronic for I2, plus U, well, plus, let's call it the ZPE for I2, minus 2 times U for translations for the iodine atoms. And then there's no rotations, there's no vibrations, there's no electronic contribution, but there will be maybe, no, the ZPEs are also 0, so everything else is 0. And so that just becomes U translations minus 2 times U translations for I, plus U rotations for I2, this is for I2 too also, plus U vibrations for I2. There is no there is no electronic contribution to the energy for I2, plus EZPE for I2 per mole. This is just 3/2 nRT, right? And this is just 2 times 3/2 nRT. And so that's equal to just minus 3/2 nRT. That's the translational contribution. And so we have minus 3/2 nRT plus, let's plug in the formula now for the rotational contribution from I2. That's just nRT. Let's plug in the the vibrational contribution for I2. That's nR theta vibe, e to the minus theta vibe over T, over 1 minus e to the minus theta vibe over T, plus now the ZPE energy for I2. And now we can just plug numbers in. That's minus 3/2 times 2479 plus 2479. So that's just 5/2. No, I take that back. That's minus, that's just minus 1/2. Well, let's just leave it the way it is. Plus, now n is 1, so 8.314. Theta vibe is 308 for I2, e to the minus 308 over 298.15, 1 minus e to the minus 308 over 298.15, and, oops, and that, plus the ZPE factor, which is 149,000. It's minus 149,000, sorry. It's minus the D0 value. So that's minus 149,000. And altogether that gives us, when we add everything all up, minus 148.83 kilojoules per mole. You can see that most of that minus 148 is the ZPE factor here, which we have to keep in this case because we've got more than one chemical species going on. Okay, so that's the delta U. We now have the delta U value. The next thing we can do is get the delta H value. Delta H is going to equal delta U plus delta PV, but we've already seen that delta PV here is delta nRT for an ideal gas, which is delta N times RT, which is minus RT. So delta H, is just equal to delta U, which we now have, minus RT. And that is equal to minus 148.83 kilojoules minus 2.479, also in kilojoules, and that is equal to minus 151.3 kilojoules per mole. Last value is delta S. There's a number of ways we could calculate this like I talked about last time, but let's do it in kind of the simplest way. So I can't just write it down, let me derive it. We have that delta G is equal to delta H, right, minus T delta S. So there's the quantity we want to solve for. Delta S then is equal to delta H minus delta G over T. All right, so now we can just plug in. We have all these values on top. So delta S R for reaction is just delta H, which is minus 151,300 in joules, minus delta G. Where is that? That's minus 121.21. Yes. So that's minus 121,210 divided by 298.15, and that turns out to be minus 100.59 joules per K per mole. That number can be compared also to the tables. If we do that calculation, that's over here actually. Let me spread this out so it's easier to see. Here's the table calculation, again using the absolute third law entropies of formation, and you get minus 100.9. So we're only 3/10 of a tick off in our calculation. That's very good. Also, I didn't point it out earlier, but this value for delta H can also be compared to the tables. So let's do that. Here's the table calculation over here, and we get minus 151.2 from the tables. So again, our calculation from first principles here, it matches extremely well with the measured values. And that is it for number 4. We just went through all of the thermodynamic calculations you're pretty much possible to do, at this point at least, with the stat mech that we know, for a chemical reaction. It was a particularly simple chemical reaction, but still, it was a chemical reaction. Next time, we're going to do it for a somewhat more complicated chemical reaction, an H2 and a Br2 going to 2 HBRs. But that's for next time.